Okay. Well, unless you all have homework questions, it's once again going to be a light week. Um, how's it coming? Oh, okay. With like homework one, like problems one, two, and three. No.
Yeah.
Okay.
I'm working on the code.
Oh, okay. All right. So, all right. So everything's hunky dory, going smoothly.
Yeah.
That's never happened before.
Code might mess up sometimes.
Yeah.
Okay. Okay. Yeah. No, this is a little unusual, but okay, great. So, um, I guess, yeah, in the past, in between just covering regular stuff, I've had to devote like whole class periods to giving MATLAB tips and so forth. And,
Yeah.
um, so, okay, well, um, we'll see how things go then. Okay, so, well, now what I'm wondering is, because again, this is what's on the schedule for the week. Um, and, uh, okay, so I can play this two ways. So this is what I'll do today. Um, and th- I don't know if I want to, I'm worried about having a situation where I open up time, now or this week for homework questions, but then you guys aren't to that point yet. And then say, next week or a couple weeks, like, oh, now it's questions, but I'm covering stuff. So, um, so I guess I should leave it to you all to tell me uh, what you prefer for Thursday. That because I can either just continue through material um, or uh, or leave that open in case of homework problems. So that depends on how you all are proceeding. Like if you don't think you'd be to that point by then now next week is fall break, so we're only going to have one class anyway. So okay, all right. I think I'll cover stuff that because it might not, it might still not fill the time. So okay, um, yeah, because the last couple of Thursdays it's like I peek in a room like, oh, nobody here. Okay, so um, free time. It's like, so I'm not sure why I took it away from myself this time, but whatever. But again, it gives me flexibility later. Um, okay. Um, now we're looking at correct methods for whenever AX equals B problem comes up as a result of spatially discretizing a PDE such as Poisson's equation. Okay. Um, now the most general approach about we've seen before is Gaussian elimination. Pivoting. So for a matrix that doesn't have any special properties um, to take advantage of, and that's going to be the way to go. So then you have PA equals LU is the LU decomposition, where P is a permutation matrix. That is used to rearrange the rows of A so that the LU decomposition exists. Um, and then you solve, then you obtain X by forward back substitution. That's covered in like 461, 561. If A is symmetric positive definite, right? And refresh your memory. That's where X transpose AX is strictly positive for all non-zero X. Equivalently, is a symmetric matrix that has all positive, strictly positive eigenvalues. Okay, so in that case, you have a couple of options. You have the Cholesky factorization. A is equal to GT transpose, or it could be thought of this way, R transpose R. The point is, whatever matrix is on the left is lower triangular. So the G is a lower triangular matrix, or R is an upper triangular matrix. So it's still lower triangular times upper triangular like you have here. It's just that because of the symmetry, the two factors are transposes of each other, and they're required to have positive diagonal entries. Okay. And closely related, the LDLT or LDL transpose factorization, where L is, and I don't know, it seems no place. Now you try to use any class where I cover this sort of thing. Lower triangular and all diagonal entries are 1. So it's unit lower triangular because I don't feel like writing out unit lower triangular. And then D is a diagonal matrix. In this case, it would have positive diagonal entries. And that's closely related to Cholesky. That we could say G is equal to L times D to the 1/2. So this is why it's called square root 3 Cholesky. Because the algorithm for Cholesky factorization requires taking square roots. And it may not seem like a big deal, but keep in mind, if you're doing any operations that are more sophisticated than abstract multiply and divide, like sine, cosine, square root, exponential, each one of those requires several floating point operations because it's computing some approximation to that function. What it does under the hood, I honestly don't know. It's probably a Taylor approximation or something based on a root finding method that's supposed to have a rapidly convergent iteration. Whereas it's possible to compute square root using a rapidly convergent iteration based on Newton's method. But no matter how efficient it is, it's still several operations. So that's why using those kind of functions are is discouraged when there's an alternative that uses only the 4 basic arithmetic operations. It reminds me, I saw an article some time ago that this game developer actually invented a new algorithm for computing x to the minus 1/2. So the inverse square root. So that's something that doesn't normally get a lot of attention. Like there are methods for doing that out there already that are meant for more general functions, but they focused on the inverse square root. And the reason why is for a game, you have graphics, you are working with vectors all the time. Often you need to normalize a vector, so you're dividing it by the square root of sum of squares of all the components. So you're scaling a vector x by the sum of squares raised to the minus 1/2 power. And their iteration basically uses Newton's method. But what was different in their approach is they had a better way of getting an accurate initial guess using a logarithmic function, actually. So, and I guess I figured it was worth the trouble to make that a little bit faster because they're using an operation all the time. Okay, wasn't planning on talking about that today, but all right. Okay, now in all of these cases, what do we have in common? You're factoring A or some shuffling of A into lower triangular times upper triangular. Same with these. And then you're solving simpler systems involving using forward substitution if you're working for lower triangular matrix, or back substitution if upper triangular matrix, or in the case of diagonal matrix, you're just performing n divisions. Okay. Now, it's important to use B's when your matrix is symmetric, positive, definite, instead of more general Gaussian elimination, because it exploits symmetry. So it takes half the flops or floating point operations of Gaussian elimination. So that's significant savings there. Okay. Now, if you're in MATLAB, the function you could use to solve a system with whatever matrix, the function name is ML divide. It's short for matrix left divide, but you would know it as backslash. So backslash is an operator that actually calls ML divide. So you could also do ML divide parentheses A comma B, and that would be equivalent to A backslash B. Okay, so what this backslash operator does is it will examine the matrix A first, and so if it detects that it's symmetric, then I don't remember offhand, but I believe what it does is LDLT factorization. LDLT is good for symmetric matrices in general, not just positive definite. But then in that case, D might have, can have positive or negative diagonal entries. And if not, then Gauss elimination with like partial pivoting. Or if the detected matrix is already triangular, then it knows to do forward or back substitution. So it sizes the matrix up first and then picks the appropriate algorithm. So it's all done very, very seamlessly. One of my fellow graduate students at Stanford said that the solution of AX equals B is A backslash B. All numerical methods are just propaganda. Okay. All right. Let's see. Did you take 561 in spring?
No.
Okay, so this is your first time seeing this stuff here, but you would have seen it before, right? Or, oh, really? Dang, okay. Well, because next time you can take 610 and get the whole story. So, okay, whereas you would have seen, maybe not all of this stuff, but a good chunk of it in 461. I don't think I talked about this.
I didn't recognize it.
Okay, I may have mentioned it, so, okay. Well, unfortunate asymmetry here. Okay, so, sorry about that. For some reason, I thought that, okay. Okay. Now, any questions about any of this before I go to the next board? Now, sparsity is a major concern when solving A equals B, where the matrix A comes from discretizing a PDE because those kind of matrices, versus especially if you're using, for example, finite differences to approximate your derivatives. They come from a PDE. A is usually sparse, meaning most of the entries are zero. Finite difference, finite element, finite volume methods all produce sparse matrices. But not all PDE solving methods do. For example, for spectral methods, the matrix is usually dense. So dense is the opposite of sparse. So in that case, most of the entries are non-zero. Although it might be sparse in another basis. Like if you use a Fourier transform to go from physical space, X, to frequency space, then spectral methods give a sparse matrix, and the other kinds don't. Meshless methods that some of our faculty here work on, Dr. Chen, Dr. Tian, Dr. Zhu, those also produce dense matrices. So it just depends on the approach to spatial discretization that you have. But for now, we're going to deal with sparse matrices, and that's what you'll put up with most of the time in the homework problems. Now, the problem is, on one hand, some kind of pivoting is usually needed. Now, if you're performing Gauss elimination or something similar, it may not be absolutely necessary to interchange rows. Like you would see this in your first linear algebra class where you're doing row operations by hand on a small matrix. You find like, oh, you're about to divide by zero if you perform the usual row elimination operations. Let's interchange rows. Okay, that happens, but it doesn't happen very often. But a more significant reason for interchanging rows is that it helps reduce the propagation of round-off error. Okay, so I'll give an example of this. The main step in Gaussian elimination is something of this form. There's some entry of your matrix that you're updating when you perform a row operation. So where this comes from is you're setting row I equal to itself minus this multiplier Mij times row j. So you're subtracting a multiple of row j from row I to eliminate Aij. Now, when you perform a row operation, of course, you have to act on the entire row. So this is carried out for each column k. So k starts at column j plus 1, goes all the way to n. Right. Now, what can go wrong is every operation incurs at least some rounding error. So this entry ajk, which would have been resulted from previous operations, has some error in it. Now, if Mij is large, whatever error is in here gets amplified by this, and that makes future operations more erroneous. So the purpose of pivoting is to make multipliers small. Even a relatively simple pivoting scheme, partial pivoting, the most commonly used with Gaussian elimination, guarantees that the multipliers Mij are at most 1 in magnitude. So at least it's containing a propagation of round fair, maybe even reducing it a little bit. Okay. So this is something that's not, of course, not talked about in a traditional first linear algebra course like Nat 326, where you're doing all this on paper and with nice numbers, fractions, and so forth. It's just not an issue. But it's because of this that there was considerable debate back in the like 50s, 60s or so when electronic computers were first developed. And I'm sorry if you've heard me spout about this in either earlier in this class or in previous class, but it's an important point that they weren't sure if, even though Gaussian elimination had been in use for literally thousands of years by that time on paper, or whatever it is people wrote on thousands of years ago, that I'll check it, but I'm pretty sure it's literally thousands, like back in in China. There's some early indications of it. That with electronic computers doing the work, and now every operation having some error to it, is Gaussian elimination even numerically stable? And it was Jim Wilkinson in his round-off error analysis who confirmed that it is, under the right circumstances, like pivoting is needed to help ensure stability. Preferably complete pivoting, but partial pivoting in most cases is good enough, and it's less overhead, so that's what people use. Okay, so and that's for what we would have done if it had been found to be unstable. That's at least it's the iterative methods, which I'll talk about later. Okay, so this is a hugely important ingredient. But the other side of the coin is this. Pivoting destroys sparsity. Okay. Like the matrices that we've seen in examples, like a tridiagonal, something like that. And if you perform Gaussian elimination on a matrix like that, and you start pivoting, you will wreck that tridiagonal structure. Your matrix will have new non-zero entries in locations that 0 before. This is a phenomenon called fill-in. So fill-in is where you get new non-zero entries in your sparse matrix. So now you're incurring a whole lot of expense. You're slowing down Gaussian elimination and the other solves like forward and back substitution that will follow it. So what can be done? That means reconsidering pivoting strategies. One option is called scaled partial pivoting. So in partial pivoting, you insist that all the multipliers are less than or equal to 1. Maybe you relax that requirement a little bit. Maybe you're okay with them being a little bigger if it means you can have a matrix that's more sparse than it would be otherwise. Okay. All right. Questions about what I've written here? Oh. It's busy how much I can yammer about numerical linear algebra and feel like I'm not saying a lot much. Never know about the PDE person, but that's because my advisor, she knows, the ultimate numerical linear algebra person. Okay. So a helpful function in MATLAB called SPI That can help you see how sparse the matrix is. So I'll give you an example of how it can be used. So if you have some matrix A, and you use MATLAB's LU function, so that performs Gauss elimination with partial pivoting, and that will return three outputs: so lower triangular factor L, upper triangular factor U, and then permutation matrix P. So this is a relationship PA equals LU. Okay. So what you can do is you do SPI of L, and certainly you can do SPI of U afterwards. That will produce a figure window that highlights where the locations of the non-zero entries in blue, everything else white. So if you have some matrix A that is sparse, so you can you SPI on it too, and you want to check okay, to see how sparse this is, how sparse are L and U, and if there's a whole lot of pivoting going on, you might find that the percentage of non-zero entries in the appropriate triangles of L and U might be much greater than what you see in A. There's a number function, N and Z A, that will print out for you the number of non-zero entries. And what might be of more interest to you is if you do that, divided by num L, which is the number of elements in A, so rows times columns. So that would be the percentage of non-zero entries that we have. So that'd be a good idea to check for percentage for A, and then the percentage of L and U. Although in case of L and U, you might want to double it because you have one triangle that's already zero. So it's kind of cheating to include that in the percentage. If there's a significant increase in the percentage of non-zero entries, then you might want to do something differently. Okay. In fact, when you use SPI, it will print out in the figure window the number of non-zero entries. The rightly figures tend to be interested in that anyway. Now, one way around the destruction of sparsity by fill-in is if you perform some row interchanges or column interchanges, because you can keep a system equivalent as long as you take the appropriate actions on if you rearrange the rows of A, you need to rearrange the rows of B also. But the question is, how do you know what row, how to rearrange the rows? So that will happen. Unfortunately, MATLAB has functions that can help with that. So okay. All right, so here's a MATLAB function, call AMD, and also for symmetric matrices. Instead of AMD, these produce permutation matrices. That you can use to try to preserve sparsity. So it tries to figure out what's best. Now, the second one is only for a case where A is symmetric. if A is symmetric, very important, any rearrangement you make of the rows must be applied to the columns. You must rearrange rows and columns the same way so that the scrambled matrix is still symmetric. Otherwise, you're going to incur twice as many floating point operations solving a system because you just lost the symmetry. So never lose symmetry. Now, in some cases, I think I mentioned this from before, is a way of rearranging rows and columns called red-black ordering. And all that means is you're just labeling alternating rows or columns, red or black. And you're just grouping all the red rows and columns together and black rows and columns together. In certain limited situations, that can lead to a more favorable structure for solving X equals B, especially with regard to certain finite difference cases. So it's something to be aware of. All right. So the idea here is at least you can't get rid of fill in altogether, most likely, but at least you can keep it in check. If you know your matrix is symmetric, positive, definite, theoretically, you don't need to pivot. You would never be in a situation where you might risk dividing by zero. Now, the issue of having propagation of rounding error could still be a problem. But I guess you won't take your chances of that. The symmetric positive definite case, I guess you could try not pivoting and see how it goes. All right. Any questions about how these work? So I guess in the homework, when you create your finite difference matrix, it's not going to be very interesting, but you try spy on it, and you can see, you should see that just 3 lines, like for the 3 non-zero diagonals that you have. And if not, you did something wrong. All right. Okay. All right. Preconditioning. Now, if your matrix A comes from spatially discretizing PE, chances are it's ill-conditioned. Okay. So to refresh your memory, I'm referring to the condition number, which is normally written kappa of A, which is the norm of A times the norm of A inverse. So it's only defined for invertible matrices. Now, I have not specified which norm. You can define a condition number for any norm. In MATLAB, you can use a con function to compute the condition number. The condition number in the 2 norm is equal to the largest singular value of A divided by the smallest. So that's the definition of a condition number. But what does it mean? It's a measure of sensitivity. How sensitive is a system Ax equals B to changes in A or B? So the idea is if A or B, if any variance should be changed by a certain magnitude, so order epsilon, so it could be a small change, then X, it can theoretically can change by an amount that's how much you change A or B, amplified by the condition number. So this is why we do not want the condition number to be large. If it is large, then it is possible that a tiny change in A or B could lead to a massive change in the solution. And actually, here's an example in chapter 2 of my book, where, all right, it was contrived, because it's possible to figure out using the singular value composition of A, what is the worst case situation of like a change in B triggering an exorbitantly large change in the solution. Now, those are like extreme cases, but still, if the condition number of A is large, basically you're talking about losing accuracy in your solution. So whatever error you have in A and B, that error could be much larger in X. And what if you use X in later computations? Then you're throwing those off too. And the thing is, if the problem is too sensitive, then you really can't trust any answer you get. Now, conditioning, I want to emphasize though, is a property of the underlying problem, not the algorithm you're using to solve it. But what that means is, if a matrix is ill-conditioned, this is issue for any method that you would use to solve it. So it's not a matter of like, this algorithm is susceptible to bad conditioning, I'll just use this one instead. No, you're in the same boat unless you change the problem. All right. Fortunately, there are ways to do that. And that's what preconditioning is about. You're trying to transform a system Ax equals B into an equivalent system where the condition number is smaller. The thing about how pervasive this problem of conditioning is for PDE specifically. So if the number of grid points, capital N, increases, this number increases too. And people are always wanting more and more spatial resolution. Well, that makes the problem even more ill-conditioned. And it could lead to this paradoxical situation, because you might think, as computers get more powerful, we can have more grid points. We have enough memory for that. We can have finer spatial resolution. And because computers are more powerful, we can compute everything more rapidly, even with this greater resolution. But because those larger systems are more ill-conditioned, that can drastically slow down or degrade the performance of methods for solving Ax equals B or other numerical algorithms that work with ill-conditioned matrices. So it might make things slower when you'd expect them to be faster, because that degradation in performance is so severe. Something, at least computing power is still increasing rapidly to try to stay ahead of that, but it's something we have to be mindful of, that a lot of algorithms in use today were developed a very long time ago, like even before we had electronic computers, like a lot of time-stepping methods for ODEs, for instance. So those are still widely used today, were invented over 100 years ago. Not built for this. Okay. So I tell people like, we should consider something different, and they're like, nah. Yeah.
All right, so in this case, we don't want the condition number to be large, right?
Right.
Okay, so at what point do we consider it to be large?
Oh, good question. Okay, there actually is a guideline for that, and I don't remember off the top of my head, but I'll find it very quickly. Okay. All right. Did or did I not? Okay. I remember seeing some relationship about like relating the condition number to like decimal digits of accuracy. Okay, maybe it's in grammar notes instead. Oh, okay. For some reason, I did not include this in my book. I'm sorry, I was thinking. Okay. Um, okay. So, that actually isn't about the condition number. Um, all right. That if you consider that, if I use U to refer to, it's called unit round off. Also known as machine precision. Generally the smallest relative error that you can hope to get. U is also informally defined as the smallest positive number that you can add to 1 and get something in the floating point system is considered greater than 1. You can get its value in MATLAB using the EPS. So EPS is actually a special predefined variable in MATLAB whose value is equal to the unit round off, which If you're wondering what is the value, it's on the order of 10 to the minus 16. So it's pretty small. And if a condition number times a unit round off is greater than 1, that's a pretty hopeless situation. Now that guideline is based on something I saw in things I was looking up. That if this does not hold, if a condition number times unit round off is less than or equal to 1, then it's possible to get a solution to ax equals b that is exact to the precision that you have. So you're always up against the limits of your available precision. And for ill-conditioned matrices, if you just do backslash and a matrix is pretty badly conditioned, the error could still be fairly large. You might have relative error maybe only 10 to the minus 7, for instance, instead of 10 to the minus 15 or 16. But as long as this does not hold, so as long as the condition number isn't that large, it's possible to do something about it. All right, and so if we can make the statement of no hope more concrete, that a procedure called iterative refinement will not come through for you, because what is iterative refinement? Iterative refinement, also known as residual correction, is you try to solve your system ax equals b, and of course you're going to get an approximate solution. So when you compute your residual, r is equal to b minus ax, which ought to be 0, but it won't be. And then you solve the number system. E is equal to r. E is the error. And that is how it relates to residual. A times error equals to residual. So if you solve that system, that gives you an estimate of the error. And then you add that onto your solution. And you go back to this step and you keep going until you achieve some convergence. We're actually going to use something like this toward the end of the semester when I talk about multi-grid methods, which actually I'll be talking about pretty soon. But it's one of the last homework problems. You'll actually use the same process, except you're going to use to carry out different steps on different grids. But the general idea is the same. Now, how well this works depends on the precision you're using for your floating point operations. So it has been shown that if you compute R using a higher precision than for the other operations, and you carry out this process, so as long as that residual is extra accurate, then your solution will converge to one that has all digits correct in the original precision. So for example, if you're carrying out your this process in single precision, so numbers stored in 4 bytes, let's say 23 binary digits, but you do carry this out in double precision, so that has 52 binary digits, and numbers stored in 8 bytes. So if you do something like that, then X will converge to a solution that has all of your single precision digits correct. So that's a way to overcome whatever ill conditioning you have. But this can't hold. So condition number times the unit round off must be less than or equal to 1 for that conversions to occur. Questions about this? I actually hadn't planned on talking about iterative refinement today, but I guess it's relevant. Not just because of this. Okay. So, all right, so preconditioning, which I've yet to talk about, is a way to try to deal with a matrix being ill-conditioned. So what is preconditioning? All right. So there's different kinds. So there's left preconditioning. So all you're doing in that case is you are probably system PAX is equal to PB. So you multiply by some matrix P. All right. Now I used the letter P earlier to refer to a permutation matrix. It's not what it is in this case. P is called the preconditioner. Okay. All right. Oh. Oops. Should have inverse here. Okay. It's also right preconditioning. So this is where you multiply A by P inverse on the right. Okay. So, instead of solving original AX equals B, you solve this system for Y. And then this is supposed to be X. Okay. So then, you can solve that system also to extract the solution of the original problem X from the solution Y of the preconditioned problem. And certainly you can do both. You can, if you want, you can have a left preconditioner P1 and a right preconditioner P2. So here's an example. 2x2 matrix to illustrate the main idea. So 1, 1, 1, 1000. Okay. Because of this large gap in magnitudes between elements, the condition number in the 2 norm of A is roughly 1001. So it's difficult to tell just a matrix is ill conditioned just by looking at it. But one feature that suggests ill conditioning is if you have widely varying magnitudes of entries. Now there are some matrices that do not have that property, like finite difference matrices. Those are badly conditioned, but all their elements are roughly the same magnitude. So, but you do have that. This can be a problem. Sometimes just scaling the rows or columns to make the magnitudes of the entries closer to one another can help. So that's actually a thing called equilibration. Okay. So here's a preconditioner I could use. All it is the diagonal of A. So then, if I use it for left preconditioning, I'm just going to scale the rows by this. So I have 1, 1, 0, 0, 0, 1, 1. So now I'm going to solve my system with this matrix instead of the other. Oh, wait, that should be 0.001. 1,000, not 10,000. Whoops. If you were to compute the condition number, again, much smaller. So if you choose the right preconditioner, it can really help. I guess one of those times where I should give a disclaimer. Your results may vary. And in fact, using the diagonal as a preconditioner, it's our simplistic strategy, but as we've seen in this example, in some cases it really can help. Actually, one of your fellow students, Samson, his research has a lot to do with preconditioning. So he uses a preconditioner that is not a diagonal matrix, but is a block diagonal matrix. Actually, it's a 2 by 2 block structure. So what are some guidelines for choosing a preconditioner? It's actually a highly non-trivial thing, despite what this example suggests. So here's some criteria. First, we want P to be a good approximation of A. That way, P inverse A or A P inverse is approximately identity. And the identity is a quintessential well-conditioned matrix. No matter what order we're using, the condition number of the identity matrix is 1. Condition number is always greater than or equal to 1. Okay. Second criteria. It has to be easy to solve systems involving P. So another way of putting it is P needs to be easy to invert. Unfortunately, these criteria compete with each other. Look at the extreme cases. If I want a good approximation of A, I can just set P equal to A. Don't have to have identity for my matrix. But it's not easy to solve systems involving P in that case, because you've made no progress in that regard. So that's a no-go. Okay. The other extreme, B is equal to identity. Can't be any easier than that to solve a system if you don't have a good approximation of A. So you're trying to find some way to balance these. All right. This is actually an active area of research in its own right. So there are people who will focus on like a particular kind of problem and develop preconditioners for that. So it's very problem specific, developing preconditioners. However, there are some general approaches that can help to at least some extent, but to have a really good preconditioner, it's difficult to come up with a general purpose one. You need to know your problem. Okay. All right. All right.
Okay, so does it mean that P is not unique?
Yeah, it's definitely not unique. Yeah. And I think only in very, very limited circumstances can you say there's any kind of optimal P. So all you're trying to do is make the situation a little better as far as with regard to the condition number. So, if I write A, I break it down to three parts: D plus L plus U. So D is the diagonal, L is the lower triangle, so not including the diagonal, strictly lower triangular, and U is the strict upper triangle. This is helpful notation to describe certain preconditioners and also, as we'll see later on, iterative methods. Okay, so popular preconditioners are like the example I just gave on the last board. Just let P equal the diagonal. Certainly, it's easy to solve systems involving D. Whether it's a good approximation of A, that depends. Like what if A is what's called diagonally dominant? So the entries in the diagonal are much larger than the off-diagonal entries. Then this is a good choice. Another one is D plus L. It's still easy to solve systems involving P because it's D plus L because you're solving a lower triangular system. So it's an order of magnitude less work than solving systems involving A. Okay. All right. So again, so these preconditioners are best if A is diagonally dominant. Can also be good for symmetric positive definite. Now, symmetric positive definite matrices are not necessarily diagonally dominant. However, the largest entry of a symmetric positive definite matrix has to be in a diagonal. So even if it's not diagonally dominant, there is sort of a bias towards the diagonal. So I'll include that as a category, which these kind of preconditioners can work well. But for symmetric positive definite specifically, there are maybe better choices. Because for one thing, using D plus L gets away with symmetry. Okay. Now, another option is called the incomplete LU factorization. So the idea is A, instead of computing the true LU factorization, A equals LU, it's L tilde U tilde, where L tilde and U tilde are meant to be sparse. Okay, and for example, what you might decide is if certain entries of A are below a certain threshold, like they're sufficiently small, you ignore them. So you could say that L tilde, U tilde are the true LU factors of an approximation of A that is more sparse than the original. Okay. In MATLAB, we have a function LU inc that carries that out for you. For symmetric positive definite case, there's also incomplete plus B. And so there's a similar MATLAB function, I think it's called cholinc, that does the same thing. Okay. You know what? I'm not sure if those functions, there's been some change in these kind of functions in MATLAB. I want to make sure my information is current. Oh, it's not. I thought, okay. Ah. Oh boy, I hope I don't have it in my book. Okay. Okay. Not that I can see anyway. So no, now there is a MATLAB function for incomplete LU. It's just not called LU inc anymore. It's called ILU. And it's I troll for incomplete Cholesky. Yeah, and actually, I think Samson's uses one or both of these in his research. Not as helpful as we would like, but I guess it depends on the problem. Okay. But there's various ways to configure them. So what I've given here is a seriously watered down oversimplification of the main idea behind incomplete LU. So I guess I'm gonna have to update my notes since the name of a function has changed. Dang it. Okay. All right. So that's the main idea behind preconditioning, at least for direct methods. Next, I'm going to get into iterative methods where preconditioning will reappear. Right. Just realized if I on my computer, I hope I didn't tilt the screen. Okay, because just I guess Nemo's going to be watching us later. Okay. So questions about anything? Also, a general reminder, since everyone here is a GTA, it's possible, I believe, to sign up for spring classes now, so make sure you don't take too long at doing that. You may not have to worry about classes filling up, but at some point, Sharon will nag you about tuition waiver paperwork and all that, so don't let it drag for too long. Well, I'm sure she'll let you know, but yeah. Okay, so, Bill Paris Day. Whoops.